Welcome to podcast number 18, where we're going to do a pretty in-depth titration problem. And so make sure that you set up another titration problem and follow along with basically the same steps that we're doing in this one to see if you understand everything. So not only do this one, but look up another problem and make sure that you can do the same stuff that we did here, as titration problems can get relatively complex pretty quickly. Okay, so our sample problem here has morphine, and morphine happens to be a weak base. Okay, and I'm going to tell you that I made a mistake by choosing morphine because I'm going to have to write Ch14.18 several times. It's going to drive us all crazy. But it's a weak base, and we were given a Kb. All right, it starts off by asking us to, all right, we're going to titrate it with a strong acid. So this is going to be, right, a weak base, strong acid titration problem. That's the first thing to do when you get a titration problem, is note what type it is. All right, we're going to titrate 50 mils of 0.15 molar morphine with some 0.1045 molar hydrochloric acid. So let's look at all of the different things that they're going to want us to do in this problem, as there's going to be quite a bit. Part A wants us to write the balanced net ionic equation for the reaction that takes place. So first off, I wrote the molecular reaction, right, which is just the reaction there on the top. Then I separated out all of my ions. Then we're going to cancel out any spectator ions, which in this case are the chlorides, and thus we are left with our net ionic equation. If we're not 100% sure, remember that a net ionic equation, this should be, right, the base plus our H plus is going to be in equilibria with its conjugate acid, HB, which is what this is. All right, now it asks, what species are present at the equivalence point? Right, and this can be a little bit difficult, and we're going to see it as we do the math a little bit later on for calculating stuff at the equivalence point. But just kind of reading through what it says there, right? It says that at the equivalence point, our morphine is converted to its conjugate acid. All right, now you would think, okay, at the equivalence point, all of the morphine has been used up, right? Because we have an equal number of moles of morphine and acid reacting together. So if you're going to say 1 mole of each, if you subtract 1 mole from 1 mole, you're going to get 0. So you'd think, okay, none of that is left. Okay, but we are producing some of its conjugate acid here. And that conjugate acid, right, it's going to be the only thing that's present for a millisecond or so, and then it's going to ionize itself and make some morphine and some H+. So realistically, right, all species are going to be present once we are at the equilibria point, or the equivalence point. Well, part C wants to know what volume of hydrochloric acid is required to reach the equivalence point. Okay, this volume will be important later. All right, and so notice that I'm going to calculate it now, and then we're going to use that somewhere a little bit later on in our problem. So if I want the volume of hydrochloric acid to reach the equivalence point, all right, well, we need to remember that, right, at the equivalence point, the number of moles of our acid, right, are going to be equal to the number of moles of our base. And these are for the reactants. And so this is my morphine, which is Ch14.18 All right, so I need to know, if I know the moles of my morphine, I can find the moles of the acid. So let's say that I have the number of moles of morphine. Good Lord, right? I told you I made a mistake that I'm going to have to write out morphine so many times. All right, this is equal to 0.0500 liters. All right, so 50 milliliters times its molarity, which was 0.1500 moles per liter. All right, it just so happens that there is 1 mole of HCl per 1 mole of morphine. Right? Because they're 1 to 1. And so we're going to end up with 0.0075 moles of our HCl. It wants the volume of HCl. So the number of moles of HCl divided by the molarity of HCl will give us the volume. All right, so we're going to do our 0.0075 moles divided by, all right, its molarity in the problem, if we go back to our problem, was 0.1045 moles per liter, and we're going to end up with 0.0718 liters of HCl. All right, which is also 71.8 milliliters, just in case they wanted that. So we're probably, like I said, going to use this value here later on. So let's remember that we're going to probably use that later. All right, D asks, what is the pH of the solution before any HCl is added? All right, so this is just a weak acid problem, because the only thing present is our morphine. So let's set up an ice table where we've got our morphine, Ch14.18O3N. All right, it is going to react with some water, and we're going to produce our Ch17H19O3N plus and hydroxides. And we got our ICE. All right, so initially, right, my molarity of my morphine is 0.1500. My water, I don't care about because it's a liquid. I don't have any of the conjugate acid, and I don't have any hydroxides yet. Now then, the change. Okay, so the morphine is going to react, so it's going to go down by some amount, and my conjugate acid and the hydroxides are going to go up by that amount. All right, so we're going to add our columns together, and we're going to get these values at equilibrium. All right, so we will now then plug those in on our next slide and solve for our pH. This says that we started with a base, all right, which meaning that a base was our reactant. All right, and so if a base is our reactant, right, remember that we're going to do a Kb problem. And Kb from the problem itself was equal to 7.4 times 10 to the minus 7th. All right, and we know that our Kb is going to be equal to, all right, well, our OH squared divided by our base concentration. So I have 7.4 times 10 to the minus 7th, right, is equal to, all right, x squared divided by 0.1500 minus x. All right, can we ignore that x in the denominator? Well, what I'm going to do is I'm going to look at my KB, and I'm going to divide that by my concentration of base. So 7.4 times 10 to the minus 7th divided by 0.1500 is 4.9 times 10 to the minus 6th. And that happens to be less than 2.5 times 10 to the minus 3rd. So yes, we can, thankfully, ignore that, which means that we don't have to do a quadratic. So 7.4 times 10 to the minus 7th is equal to x squared over 0.15. All right, now we can solve for our x, which is also our OH concentration, and we get this to be 3.3 times 10 to the minus 4th. All right, so then the POH is the negative log of that, and we get that to be 3.48, but we want the pH, so 14 minus 3.48, and we get that to be 10.52. All right, took us a while, but we got there, right? But remember, this is still just doing a weak base problem. So now we want to figure out what is the pH of the solution halfway to the equivalence point. And as we worked out earlier, we saw that right halfway to the equivalence point, we are going to have an equal amount of the weak base and its conjugate acid, and we decided then that the pH was equal to the pKa. All right, well, we have the Kb, and remember that then we could find the Ka, right? And so what we're going to do was we're going to take our Kb, which is 7.4 times 10 to the minus 7th. We're going to solve for a Ka, which is 1 times 10 to the minus 14th, at our Kw divided by our 7.4 times 10 to the minus 7th. And I get 1.35 times 10 to the minus 8th. And so the pKa is the negative log of that. And so our pKa is 7.87. Yay! All right. Now, lastly, we're going to move on to F. Right? And F makes us have to think a little bit about what's happening here. And this is where we're going to go back and use that volume that we found much earlier in part C. It says, what is the pH of the solution at the equivalence point? Okay, so if we think about at the equivalence point, right, we have converted all of our morphine into its conjugate acid, right? But we've converted it all into that acid, but now the acid is going to partially ionize itself and become some H plus cations and morphine. This is a weak acid. This will be a weak acid problem. All right, well, we have our weak acid problem. That means that, right, I'm going to set up an ice table. Well, I know that I'm going to start with the initial amount of this is 0.0075 moles, but I want this to be in concentration because I need concentrations to plug into our weak acid equilibria constant problem. So this is moles divided by our liters. All right, well, we started with, right, our 50 milliliters, 0.05 liters. But remember that to reach our equivalence point, we added in, right, 0.0718 liters. Right, we added that in to get there. And so our initial molarity before this now reionizes is 0.062 molar. All right, let's set this up in an ice table and finish off this problem on our next slide. So here we've got our ice table where we've got our initial, our change, and our equilibria. And so as we just found, we're starting with 0.062 molar of that. Before it ionizes, we're going to say that we have none of our products. It is going to ionize and go down by X, and our products are going to go up by X. So we end up with this. All right. We have a weak acid as our reactant, which means that we need to do Ka is equal to our H plus squared over our weak acid in this case. We found Ka already to be 1.35 times 10 to the minus 8. Right? We found that when we were finding the pH at the equivalence point. Our H plus is going to be X, and we're going to square that. Our HB is going to be our 0.062 minus X. Well, I'm just going to say that this is going to be, the X is going to be small enough that we can ignore that in our denominator there, so we don't have to do a quadratic. And so my X then, which is equal to our H plus, is 2.9 times 10 to the minus 5th. And finally then the pH is negative log of the 2.9 times 10 to the minus 5th, 4.54. All right, so I'm going to tell you, right, whether it be strong acid, strong base, weak acid, strong base, or strong acid, weak base, right, we want to be able to calculate pH before titration, pH at 1/2 the equivalence point, and the pH at the equivalence point. Those are standard questions about titrations that you might see. All right, so we did it for a weak base, strong acid here. Make sure that you can do the other two types just in case those show up. All right, that ends another podcast. Our final podcast is just going to go over some loose ends about thinking about our acids and bases, a little bit outside the box, right? It's going to be another one of those types of questions that I really like. We got to think about what we're mixing together and what the pHs are going to be then.